This is the video on the complex form, the trigonometric form of a complex number. A complex number has a real, what we call a real, and imaginary component. We write them as a plus bi. The complex number system is really what we operate under. We spend most of our time under the real system, but we also have to consider what they've kind of misnamed as the imaginary. Every number is really complex. Like for instance, 5 is technically 5 plus 0i. It doesn't have an imaginary component. Or 4i is really 0 plus 4i. Every number can be written in this form. In our work, we're going to have the real and the imaginary axis. So if I graph -2 plus 5i, I'm going to go back 2 on the real axis and down and up 5 on the imaginary axis. And this dot actually shows me where this number is, -2 plus 5i. Now, they have what's called, our book and many books call it the absolute value of the complex number. So the absolute value of this, or the absolute value of a plus bi, is equal to the square root of a squared plus b squared, which actually gives you the distance from the origin. The reason it's called absolute value is all about distance. Like for instance, this is 4 units from the origin. This is -5 units. In other words, this is 5 and this is 4. If we're talking about distance, we're talking about the absolute value. That's 5 units from the origin. So technically, we're going to find out how far this is from the origin. You don't have to draw an arrow, but in physics, that would be a vector that has magnitude and direction. This absolute value is also the same as the magnitude of the vector. You don't have to use those words, though. So we really want the length of it. So we have these sides that we don't draw, -2 and 5, that are our a and b components, and we want the absolute value of it. So we say the square root of -2 squared plus 5 squared. That would give me the square root, if you could read my writing, of 29. And so the magnitude or length of this vector, and we call that r in a lot of our work. Just like we've called this the x component, the y component, and we call this r. So we're talking about thetas and r's here. Theta is how far you rotate, and r is how far you go to get to that component. All right, now in looking at a triangle anywhere, or imaginary number anywhere, like say this one, if I draw this, we have a component, b, and r, which is the length or magnitude or absolute value of the vector. And this is our angle, and here's our reference angle theta that would tell us everything, or well, this is our angle really, theta. And of course we depend on the reference angle, but that's theta. All right, now we know the cosine of theta is x over r, adjacent over hypotenuse, So cosine theta is a over r, and sine theta is b over r. And so then I can multiply these and get this result. I can say a is equal to r cosine theta, and I can say b is equal to r sine theta. And we're really starting something actually that we'll study more later called polar coordinates, where in polar coordinates you have a radius that you go and a theta that you turn. These are really important. What I mean by, to get to this dot, I could do my a and b components, or I could turn an angle theta and go out r and get to the same dot. So this is a trigonometric form of a complex number. So if I fill in these facts, a plus bi, the trigonometric form of a complex number is a is r cosine theta, and b is r sine theta times I. I don't really need to put those in parentheses, but all right, then we factor out the r. And so we have cosine theta plus I sine theta. It's better to put the I in front of the sine theta so you can really see where it is. And this is what you're going to need to know, the main thing you're going to need to know for homework. All right, so there's some good examples in your book, but again, this is the that's a star. This is the trigonometric form of a complex number. This is the rectangular form of a complex number. But what's absolutely wonderful is this trigonometric form, ironically, is easier to work with than the rectangular form. So if we're going to write the trigonometric form of a complex number, and we know our complex number, a lot of times they're called z, it doesn't really matter, is negative 2i. That means I have 0 minus 2i. This is a, and this is b. So I need to find r. R is always this distance, and so you do the Pythagorean theorem with your a and b components, the square root of a squared plus b squared. So r in this case is the square root of 4, which is 2. And the radius we've said is always positive all year long, or yeah, since we started trig. And so now I know my r is 2, so I'm going to have 2 times cosine theta plus I sine theta. Now I need to know what theta is. Theta is pretty easy here. If I have a negative 2i, that means I have 0 minus 2i. That means that I've gone right down here. And I can see that angle is 270, or in radians, 3 pi over 2. You also could have said, it would have been fine to use negative pi over 2 also, but a lot of times, well, it doesn't matter. I would take either one, so they're not really unique. Different people could have different things. So in a minute, I'll do another one and we'll verify that works. All right, so let's do another example. Let's use, we're going to write the complex form for this rectangular form, 2 minus 2 root 3i. All right, so I need r and theta to do this. So I'm going to say r cosine theta plus I sine theta. All right, r is found by saying the square root of a squared plus b squared. And so that gives me the square root of 4 plus, this gives me 4, if you square 2 and square root of 3, you're going to get 12. So you get the square root of 16, which is 4. So my r is 4. And now I need my theta. All right, now my theta, what's happened is I've gone back 2 and down 2 root 3. So I'm in the third quadrant down here. 4 is this distance. But I need to know what this angle is, okay? So it's a lot like your x and y components, your a and b components. So my x or a component is negative 2, and then I went back 2 and down 2 square root of 3. So there's a few different ways to do this, but I'm going to do it, I'm going to do it this way. You could do something like tangent of theta is opposite over adjacent, or your b component over your a component, your y over your x. And so this distance was negative 2 root 3 over this side, which was negative 2. So you have tangent theta is root 3, which tangent can be positive in first and third quadrant, so we know we have a pi over 3 degree angle in the third quadrant, which would be 4 pi over 3. There's a few different ways to find that would always work out for you. Like, for instance, you could have used sine. You could have said opposite opposite over hypotenuse, and you would have also gotten 4 pi over 3. It would work any way that you did it, but we usually use tangent. So that we just use these two components. This is the A is like your x, and this is like your y. And you know tangent is y over x, or b over a in this case. All right, so this would make somebody do this. Rectangular form, you would go back 2 and down however far negative 2 root 3 is. This would make somebody do this. This would make them rotate 4 pi over 3 radians and walk out 4 units. Do you see you get to the same dot? One's trigonometric form of a complex number, one's rectangular form of a complex number. Also, you can verify that it works like this, like you could check it. You could say 4 times the cosine of 4 pi over 3, if you were on a quiz, would be negative 1/2. The sine of 4 pi over 3 is negative square root of 3 over 2. Distribute, you get negative 2. This gives you I, and this would give you negative 2 root 3 if you cross out your 2, which is the same. You should be able to go back and forth from rectangular to the trigonometric form, which later on is like the polar form. Okay, but you could have just stopped there. All right, so now we're going to go the other way. We have the polar form, the trigonometric form, which is this. Okay, and so that gives me, so now I'm trying to get it back into rectangular form, which is super easy. So all you do is distribute. So you have square root of 8 times the cosine of negative pi over 3 would be 1/2. Then you have square root of 8i, and the sine of negative pi over 3 is negative root 3 over 2. So in a plus bi form, by the way, this is 2 root 2, so that'll give me root 2 plus, this is 2 root 2, so that's going to give me minus 3 square root of 2i. Okay, so if I have it already in the trigonometric form of a complex number, I just distribute for rectangular form. If I have rectangular form, I've got to find r using the Pythagorean theorem, and I've got to find theta using the b over the a with tangent. Now let's see what this picture would look like. This person would go negative pi over 3 and walk out however far 2 root 2 is to get to this dot. To do this, you would go out square root of 2 and down 3 square root of 2. That a plus bi would get you to the same location. Alright, so you can like look at the video some more, fast forward or rewind or whatever that you need to do for that. Now, this is super cool. You can also, if you write it in the trigonometric form, it's super duper easy to multiply. So if I want to multiply two trigonometric forms, you'd have R1, or let's say the first one would be R1 times cosine of the first angle plus I times sine of the second angle. And Z2, another one out here somewhere, would be R2 times cosine of the second angle plus I times sine of the second angle. So if I say Z1 times Z2, I'm going to multiply all of this together. So I'm going to say R1 cosine theta 1 plus I sine theta 1 times R2 times cosine theta 2 plus I sine theta 2. So this is all multiplied together right here. So I'm going to say R1 times R2, and then I'm going to have to do FOIL, so I just move this out here with this other R, and then I'm going to do FOIL here. So this is cosine of theta 1, cosine of theta 2. This is I times cosine of theta 1, sine of theta 2. This is I times sine of theta 1, cosine of theta 2, and this one is I squared sine squared of theta 2. Let's have R1, R2. Now, cosine theta 1, cosine theta, So I have cosine theta 1, cosine theta 2, plus, let's see, oh, I'm sorry, that wasn't sine squared. I knew I'd done something wrong. Hopefully you caught it. Okay, this would be this one right here. I messed that up. That would have been I squared, and that would be sine of theta 1, sine of theta 2. Those were different expressions. So that part I'm going to move over here. I squared, you should remember from algebra, is -1. So this one is here. This one is minus sine theta 1, sine theta 2. These both have an I in them that I'm going to factor out, and that gives me cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. It's a big pain, but something super cool going to happen with our identities. This is cosine theta, cosine A, cosine B minus sine A, sine B. Gives me cosine of theta 1 minus theta 2, because these are two different angles like A and B. This one, so that was like the, I'm sorry, I got to be careful here. Cosine A, cosine B minus sine A, sine B gives you cosine A plus B. I don't have an A plus B here, but it's the same thing. Plus I, cosine A sine B plus cosine B sine A. This is the identity for sine of your two angles added together, theta 1 plus theta 2. So this is actually wonderfully remarkable. To multiply 2, you multiply your radii together, and then you add your angles together. I don't know, I'm writing it over again. So if you have this in trigonometric form, things are going to be a whole lot easier. Like for instance, if I want to multiply these two, it looks like it would be a nightmare, but it's not. This is 3 cosine of pi over 4 plus I sine of pi over 4. This is my first point. My second one is 2, these are just in the book, cosine of 3 pi over 4 plus I sine of 3 pi over 4. And this is all you've got to do to multiply the two together. Okay, I'm going to use this. So you multiply your radii together and you get 6. And then you say cosine and you add your angles. And you get pi over 4 and 3 pi over 4 is 4 pi over 4. And then with sine, you also add your angles. Sine of pi. And that would be your answer. If you needed to write it in rectangular form, this is in the trigonometric form of a complex number. If you wanted it in a plus bi form, then you say 6 times the cosine of pi is -1. And the sine of pi is 0, so it just knocks that out. And so your answer here is just -6. And that's what happens if you multiply these two complex numbers together. So it's awesome when you, so you may want to rewind this or look in the examples in the book, but it's super good. Now I'm not going to derive in interest of time today what happens when you divide them, but the good news is if you're dividing z1 over z2, z1 would be r1 cosine theta 1 plus I sine theta 1. And Z2 would have other components. And here's what's awesome. You get to divide your radii and then just multiply it times cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So when you're multiplying, multiply your radii and say add your angles. When you're dividing, divide your radii and subtract your angles, like this. An example from the book. So let's do one more product. This is a product where they're asking me to say Z1 times Z2. So I have 2 cosine of 2 pi over 3 plus I sine of 2 pi over 3. And I'm multiplying it times 8 cosine of 11 pi over 6 plus I sine of 11 pi over 6. So to multiply them, I multiply my radii 16, and I have cosine I sine. Add your angles together, so I need a common denominator. I'm going to call this 4 pi over 6 and 11 pi over 6, which gives me 15 pi over 6, which reduces to 5 pi over 2. And you could leave it like that, or if you want to write it in rectangular form now, it's really easy. The cosine of 5 pi over 2, which would be right here, is 0. The sine of 5 pi over 2 is 1. So you would get 16i, or 0 plus 16i, if you wanted to write in a plus bi form. All right, now we're going to do a quotient, z1 over z2. I'm doing 24 cosine 300 plus I sine 300, which by the way would take you here 300 degrees and you go out 24 units, divided by 8 cosine 75 degrees plus I sine 75 degrees. Good news here to divide. Divide your radii and subtract your angles. Cosine I sine. Oh, by the way, sometimes it's called CIS, cosine I sine. So if you say 300 minus 75, you get 225. That's the trigonometric form. If you want the rectangular form, the cosine of 225 is negative root 2 over 2, as is the sine. So a plus bi would be like that. All right, your homework will be to do some of these. So pretty easy. Develop the formulas, but you'll be applying the formulas.